In-class activity 12C, shifting polynomial models. The electrical power required to run a coffee shop varies throughout the day. Which graph below might best represent the amount of power used at the coffee shop? Explain why you believe your graph is the best choice. We have three graphs, A, B, and C, and since the electrical power used during the course of the day at a coffee shop would vary, it looks like B, the second graph, choice B, would be the correct choice here. Objectives for the activity. You will understand that polynomials can be used to model quantities that vary over time. The graph and equation of a polynomial are closely related. You will be able to, given a list of roots, graph polynomials to model quantities that vary over time. Explain how a graph and equation of a polynomial are related. Apply shifts and scales to fit a polynomial to a model. Question 2. Michael would like to model the electrical power demand in his restaurant as a function of time. Based on data from the power company, he sketches the graph of a function that inputs the time in hours past midnight and outputs the power drawn by his restaurant in kilowatts. The graph is shown as follows. Part A. Notice that the graph has no horizontal intercepts since it does not cross the x-axis. It appears that this entire graph has been shifted up from the x-axis to help us determine an equation for this graph. We must first determine the roots of the polynomial prior to the shift upward. One way to help find the roots is to imagine a horizontal line drawn through the graph so that it touches the graph in several places. Imagine a line at y equals 50. Notice that we marked points on this line at 1350, 1750, 1150, and 2050. Using this information, estimate how far the graph was shifted vertically. What I'm going to do here is just draw a dotted line right where y is equal to 50. There we go. Now, the graph already has these points. I'm just highlighting them, indicated or marked on the graph. And if we think about this as the horizontal line, like y equals 50, which it is, we want to use this information to estimate how far the graph was shifted upwards. And we can see here that it's about 50 units. Part B, if we shifted the graph down 50 units, what t-values would be the horizontal intercepts? So I'm going to write t is equal to, if I move the entire graph down 50 units, it looks like the point 1150 would be a root, and we could write t is equal to 11. And then for the same reason, t is equal to 13, t is equal to 17, and finally t is equal to 20. There we go. Write a formula for the polynomial function f with the roots found in part B. So let's call this function f, and we'll write f of t is equal to t minus 11, t minus 13, t minus 17, and t minus 20. Part D, using a graphing calculator or app, graph the function in part C. Adjust the function by flipping and scaling it as needed to match the original graph. Once it was shifted down to the horizontal axis, call your new function g of t. Okay, let's go to a calculator app, and we go here. We'll go to the y equals screen, and let's enter this in under y1, and we're going to go parenthesis, instead of t, we're going to use x, remember? So we go x minus 11, and then we go x minus 13, and then x minus 17, and finally x minus 20. Let's just graph this and see what we come up with. If we need to change the window, we'll do that. Okay, I don't see anything here. And let's just do zoom standard. And I see nothing. Okay, so let's go back to where we were, and we'll go second window. And we're going to change the window. All right, so let's do the X min. Why don't we start at 10? And then the max will go up to, say, I don't know, 22. Then we'll try that one. And the scale can be 1. Y min, why don't we try 0? And Y max will go to 100. And then let's graph and see. Oh, there we go. We have something here. It's going to change this a little bit. There we go. We want to write this, and I'm going to go back here. I'm going to go back to my notability, and it says using a graphing calculator, graph the function in part C, adjust the function by flipping and scaling it as needed to match the original graph. Now the original graph is under question 2, and I'm going to go and compare it to what we just drew on the calculator, and it looks like our graph is upside down compared to their graph. So we're going to have some adjustment to do. So why don't we do this? First of all, whoops, we'll go here. I'll go on the front, and I'm going to add or insert a negative. We can even do a -1. And this is going to rotate the graph around the horizontal axis, and that looks better. Yeah, the two relative maxes are on the sides. In the middle, there's a dip or the relative min, and that is looking good. Now, the relative max, this isn't, yeah, this is crossing the x-axis, so we don't want that. Let's see what we could do. If we scale this, why don't we try scaling by, let's see. Okay, so this graph is, the graph on the calculator is too large. So let's do this. I'm going to look at the max here, the high point of this graph, the relative max, and I'm going to estimate it to be about 100. And then the low point here, I'm going to estimate about 10. From 10 to 100 is 90. So I'm just going to write a little note for myself here. 90, that's going to be the numerator of our fraction. And to come up with the scaling factor, remember how we did this in earlier videos? Well, here's our graph. Let's do the same thing. My relative max here is about 97. Well, you can even estimate it at 100 to keep it in round numbers. So 100, and then the low point, the low part here is, whoops, is, hold on, there we go, about 80. So 180. So 100 plus 80 is 180. Let's take that information back here and make it the denominator of our fraction. 90 over 180 is a half. And remember, we want to add a negative sign to that. So here we go. This is going to be function g. We're going to put the negative sign in to rotate that about the horizontal axis. We get a half, or 0.5, and then we get t minus 11, t minus 13, t minus 17, and finally t minus 20. They're the four linear factors. So part D, it says we call this function g, and let's see, adjust the function by flipping and scaling. It's needed to match the original graph. Let's just go back and check this. And I'm going to go back to here, the y equals screen, and let's make this a negative 0.5. Whoops, second insert, parenthesis, and then put in our x. So let's see what we have here. I'm going to graph. Okay, let's compare this to the graph that we have. 100. Okay. Let's see. And this looks pretty good. Remember, our graph back here, we still have to shift it up 50 units. So when we do that, let's just do that and make sure we get what we want. Done. Y equals, we have to add plus 50 and graph that. And that looks good. Let me go back here. So this is actually part E. Vertically shift your function g of t from part D so that it matches Michael's function. To shift a function up, we add a value to the end of our function, and to shift a function down, we subtract a value from our function. Call your new function h of t. So when we do that, we're going to get h of t is equal to negative 0.5, and then the linear factors are t minus 11, t minus 13, t minus 17, t minus 20, and then we have to add the 50 to the end. There we go. So I'm going to scroll all the way up here to part 3. It says use the method from question 2 to find a formula for a polynomial function that matches the function graph shown. Explain the process you used. Okay, so let's see. Here's the picture of the graph. And what I'm going to do is, I notice that this horizontal line is going to be at y is equal to 10. We can use these points here to get us started. So that means that this is, when t is equal to negative 1, t is equal to 1, and t is equal to 2. So what we could do is call this function f. We'll write f of x. And then the roots we could write as x plus 1, x minus 1, x minus 2. Now the local maximum and local minimum of this function, they're about, let's see, how many units apart? So why don't we go to our calculator. Okay, that's what we finished with that. Let me just turn that off and go here, and we'll do x plus 1, x minus 1. Oops, I forgot my parenthesis. Parenthesis x minus 2. And then we're going to do a graph. Okay, so we can't see that. Let's adjust the window. So second window. And let's see. Okay, we could even try the standard viewing window, and that's listed here. Why don't we just graph this and see? There we go. And it's going to expand on this a little bit. And okay, so let's look at the local max and min. So the max, whoops, is about 2.1. The minimum is 6.3, or I'm sorry, 0.63. That's about 2.7. There we go. Here. So let's write this down. If we take the two values, we have 2.1, and then we add 0.6 to it, we get about, well, it's going to be 2.7. And then if we look at the values here, we're up at 20, and then we're down to about, I'm going to put 20 here, and then we're down to about 7, so that's about 13, a difference of 13 between 20 and 7. So there's 13 in here. So let's write the scaling factor as 13 over 2.7. Now that's going to be about 4.8, and I'm just going to estimate that at 5. So our scaling factor is going to be 5. From here, we want to write this function as g. So let me write it as g of x is equal to 5, which is our scaling factor. Then we get x plus 1, x minus 1, and then x minus 2. Now we have to next add 10 to this. So there we go. Part 4, use polynomial multiplication to write your answer to question 3 in standard form. And then let's do this here. We're going to multiply this out. I'll just leave 5 alone for right now. We'll multiply the x plus 1 times x minus 1. We know that's x squared minus 1. We still have x minus 2, and then the plus 10. I'll continue multiplying the binomials. When we do that, we'll get x cubed minus x minus 2x squared plus 2 and plus 10. And then finally, we'll multiply everything one more time times the 5 here, 5x cubed, minus, I'll write the quadratic term next, so we'll go minus 10x squared minus 5x, there's our linear term, and then 5 times 2 is 10 plus 10, we get 20. Part 5, for each of the polynomial functions, identify the roots of the polynomial, the scale, and the vertical shift. So let's write it this way. I'll just keep track of it. The polynomial, and then we'll do the roots. We'll do the scale, factor, and then the vertical shift. All right, so we'll start with the polynomial p, and then we get t is equal to -4, 1, 7, and 11. The scale factor is the 0.0012, and then we're going to go down 14. W is next, so W of x, we get x is equal to, we get a half, we get 11/3, and 10. 3 is the scale factor, and then we go up 7/3. And we do Q next. So R is going to be equal to 0, -2.7. We get 3.6 and 8.14. Scale factor is 0.154, and vertical shift is none. That's the end of this video. Thank you.